the last class we were wondering how to make an amplifier, and the aim of the amplifier was to take a small signal Vi with the source having some source resistance Rs, and we would like to make an amplifier. In the simplest case, the amplifier is a 3-terminal 2-port, and across a load we would like to have an output voltage Vo, where the power dissipated in RL is greater than the power drawn from the source. Okay. So, we had and we were wondering how one can make that box there. The first choice was to see if that box could be linear, right, and which basically means if there were no energy sources inside the box, it basically means it is a network of resistors, right, and we immediately concluded that it cannot be linear, and simply because the power dissipated in RL is bound to be smaller than that drawn from Rs, because from Vi, because some of it is going to be dissipated inside the resistors inside the box. Then we said, oh well, yeah, that of course is pretty obvious. Why don't we do something which does not violate the first law of thermodynamics? Basically, so we have energy sources V1 and V2. Now you can't say, well, the power dissipated in RL has, cannot be smaller than Vi, because there are two sources which can provide energy. However, if you look at the voltage across RL, right, so this is clearly a nonlinear network because of the presence of the voltage sources. However, if you look at the voltage across RL, it is a superposition of 3 voltage sources, one due to Vi and one due to V1 and one due to V2. It might turn out that for specific values of V1 and V2 and for specific values of resistors inside that box, it might turn out that the power dissipated through RL can be greater than the power drawn from the source. However, we are interested in the power dissipated in RL, which is proportional to the input source, right. The power, the extra power drawn due to dissipated in RL due to V1 and V2 are simply DC power, and they basically are useless as far as amplification is concerned, right, because we want the power at the input frequency corresponding to the input source Vi, we want that to be larger, right. There is no fun in simply heating up the resistance RL by going on pumping DC power through it. Does that make sense, right? Okay. And the next job is to say, well, so therefore the box cannot be linear, cannot be a network of resistors. Adding energy sources outside also does not help. Then the next choice is to say, well, the box is nonlinear, right, and even if the box is nonlinear, it does not help if there is no source of energy outside, right, because that simply does not that will violate energy conservation, right, and therefore the only possible choice is when this box is nonlinear and we have these two voltage sources V1 and V2. Okay, there, please note that this box does not have any energy source inside. Okay, all the energy sources V1 and V2 are outside the box, and it is still not clear whether this will still work as an amplifier, but the other 3 cases will definitely not work. All right. So, we are interested therefore in making sure that the small signal, the power in RL corresponding to Vi is larger than the power drawn from the source itself, okay, and therefore, we are interested in figuring out the incremental voltage across R, correct. Now, we have a nonlinear 2 port and we have two nonlinear elements, namely capital V1 and capital V2, which are basically the energy sources. Okay. So, to find the incremental equivalent or the incremental voltage across RL, what we need to do is simply replace every element in this circuit with its incremental model, right. So, that is easy, we have already done that. What do we do? What happens to capital V1? We go element by element, it becomes a short circuit, and then of course, what happens to Vi? Vi is as is. And this is Rs, okay. And what comment can you make about the box? It is a linear 2 port. Now, the linear 2 port, as yesterday we said that we can model it by its incremental Y parameters. So, we will replace that by its equivalent network. So, that is VO. What must this be? All these are conductances, mind you, and because all these are conductances, let us not get confused. Instead of Rs, I am going to call this as Gs, where Gs is 1 by Rs, and likewise GL is 1 over RL. So, everything in this network on the right correspond to conductances. Does it make sense, people? All right. Now, before we, I mean, what we are trying to figure out is, well, we know that box is nonlinear. We want to figure out what the characteristics of that nonlinear box must be, so that we are able to get amplification, right. And before, so this must be Y21, let me call that Vx, all right. And before we get on to the job, let us try and figure out what the characteristics of a good amplifier are. Okay. Remember that this corresponds to the source, this of course is the load. For an ideal amplifier, you know, what comment can we make regarding the gain of the amplifier if the source resistance changes? For a good amplifier, we would like to make sure that the gain remains independent of source resistance. So, this is our wish list. Independent of Rs, all right. Gain, what about load? Ideally, we would like it to be independent of all right. And what else? A gain must be as large as possible. Right, and we can add things later if we find additional things that we would like. Okay. So, so basically what are we trying to do therefore? What should we try to do now? Basically we say, well, you know, this box is modeled by its incremental Y parameters, okay. if the box is modeled by its incremental parameter y parameters, we will be able to go and calculate, find an expression for the gain between Vi and Vo. That gain will be a function of Gs, Gl and all the 4 y parameters. We stare at that expression and figure out what those numbers y11, y12, y21 and y22 must be, so that we basically are able to satisfy our wish list, correct. So, the first step in the whole exercise is therefore to compute the expression for gain from Vi to Vo, okay. And since everything is what do you call conductances, it is easier to do this using nodal analysis, right. So, we write KCL at every node and we can simplify this as a current source. So, this is Gs times Vi and this is the conductance Gs. This is exactly identical to the Thevenin equivalent that we saw earlier, right. Okay. Now, if you want to write the nodal equations for this, what will you do? What are the unknowns? What are the unknowns that we are in this network? Two unknowns, which are the node potentials Vx and V0. Very good. Okay, so we will write the nodal equations. So, this is basically Gs plus y11. This is the node conductance matrix. What should be here? What should be there? How many of you are familiar with writing nodal equations? So, what are the unknowns? That must be Vx, Vo. What must be on the right hand side? Yeah, what is the current flowing into the Vx node? Gs times Vi, and this must be 0. The first term in this matrix must be first row, first column must be Gs plus y11, okay. This must be y22 plus Gl, that is easy. Then what? Okay. Then y2. Does it make sense? All right. So, what should so what is V naught therefore? What should we do? Yes, use Kramer's rule, determine replace second column with GSVI, sorry, GS plus Y11, Y21, GSVI 0, this determinant over So, what is VO now? Minus GS times Y21 times VI by GS plus Y11 times GL plus Y22 minus Y12, Y2. Does it make sense? Okay. So, that is the gain of this amplifier. Let me copy that down. I want to revert back to the original and this is VO by VI. All right. So, after analysis we have found that this is the this expression is the expression for gain between Vi and V. All right. So, now let us look at our wish list and then figure out what to do. But first thing, what is the first thing that strikes you when you look at it? Of course, it is a function of GS and GL. All right. What comment can we make when we look at the denominator? We see that the denominator is formed as a difference of two terms. So, whenever you have a denominator which is of the form A minus B, what happens if A becomes equal to B? It becomes infinite, right? Okay. So, that I mean if the gain is infinite, what does it mean? Gain is infinity, that basically means even without an input you get an output, right. So, this is basically instability, right. I mean basically you want a friend who talks to you nicely, but you do not want a friend who keeps on talking, right. Okay. So, like that you want an amplifier which has a lot of gain, but not gives you output even without an input, all right. And but unfortunately, as you can see, this A term depends on GS and GL, correct. So, depending on the source and the load resistance, it is very likely that somehow this term will become equal to Y12, Y21, right. In practice, because you are going to sell this amplifier, and for some magical combination of GS and GL, it may very well turn out that the denominator becomes 0, in which case the amplifier is completely unusable, right. And it is actually pretty easy to see for this scenario to happen, right. And I will illustrate it in practice. So, this is an acoustic 2 port, correct. So, this is a mic, and there is some amplifier here, and there are loudspeakers in this room, as you can see around you. Okay. So, remember, what is Y21? What does Y21 quantify? The effect of Y21, the effect of an excitation at the input on the output. Okay. What does Y12 quantify? The effect of an excitation at the output port on the input, all right. Now, so in this acoustic analogy, where is the what quantifies Y21 therefore? What does Y21, what determines Y21 of this acoustic 2 port? The volume knob of the amplifier, right, which my friend there is controlling, okay, all right. And what quantifies Y21 of this acoustic system? y12 I understand, but in this room where is that y12 coming from? There is a direct path from the speaker to the microphone, back to the microphone, right. Okay, this is what constitutes the y12 of the acoustic 2 port. All right. Now, if you simply, and this the gain knob here quantifies y21, right. At this point you can see that is are we getting an output without an input? No, right. Mr. Balaji, can you increase the gain? Right. So, by increasing the y21, you can see that for some value of y21, in spite of having a really nice room with this being as small as possible, right. I mean, why do you think all this fancy wood and this absorptive material is there? It is not for the aesthetics, okay. It is not only for the aesthetics, the primary reason is for to absorb the amount of feedback. I mean, basically is in our 2 port parlance, it is to make sure that this y12 is as small as possible, all right. And I am sure you have seen this scenario before, correct. I mean, you have a public address system and then suddenly it starts singing, okay. And what do you do to fix the problem? Instinctively what do you go and do? You reduce the volume, correct. Why is that working? If you reduce the volume for a given y12, you can't do anything about the y12, right. So, if you have a hall with bad acoustics, it basically means that the sound not only comes directly, but also hits walls and then all that, and then comes to your microphone through unattenuated after getting reflected through multiple walls. Now, with all this acoustic padding, what is happening? All those paths are getting eliminated largely because the sound is getting absorbed by these walls. So, the y12 becomes much smaller, but still it is possible to send the system to instability by what did we do? We simply have increased y2, all right. Okay. So, to ensure therefore unconditional stability. So, one of the attributes of a good amplifier therefore is that it must be unconditionally stable, not merely stable for some magic values of GS and GL. It must also be unconditionally stable. You are selling it out, correct. The user might put arbitrary values of GS and GL, and therefore, the 2 port must be, the amplifier must be unconditionally stable, and the only way that is possible, as you can see here, is if this term doesn't, you can't do anything about the first term, that is there, right. The only thing you can do is that the second term does not exist. So, that at least 3 ways of making that y12, y21 go away, correct. Either, so let's so for unconditional stability, right, this y12, y21 must be 0, correct, and this means there are at least 3 ways of accomplishing this. What are they? I mean, you can make y12 0, y21 0 or both 0. Okay. So, now which of these choices is the most appropriate? y12. Why not y21? Yeah, I mean, if you make y21 0, then well, there is no instability, but there is no gain either. There is there is no connection between the input and output either, correct. Okay. It is like saying if you are very poor, then nobody can rob you, right, because you have nothing to lose, correct. But that is not, hopefully that is not an ideal situation, right. So, so basically you want y12 to be equal to 0. So, if we therefore now set y12 to 0, then this term vanishes. All right, and we are left with this expression. Does it make sense so far? All right. So, then we want the gain to be independent of Gs, and what comment can you make now? What should we do if we want the gain to be independent of Gs? Well, the expression is telling us that y11 must be 0. So, by the way, if y12 is 0, this goes away. Okay. So, for a gain independent of Gs, it is very clear that y11 must be 0, right. Intuitively, why does that make sense? Stare at this picture and tell me why that makes sense intuitively. Vx is basically Vi minus the drop across the input resistance, the source resistance Rs, right. The only way the gain can be independent of the source resistance is if Vx is independent of source resistance, right. So, I mean, one way to do that is to say have source resistance equal to 0, but that is not something that is in our hands. The only thing we can do as far as the box is concerned is to make sure that it does not draw any current from the source. So, that is basically saying that the input, this y11 must be 0. So, that basically means that goes away. Okay. So, therefore, what is Vx therefore now? Vi. Okay. Now, if y11 is 0, as you can see, the gain is indeed independent of Ys. Now, we want a gain independent of GL. Is that possible? Evidently, it is not possible, right. What about for a given GL, how do we maximize gain? Minimize the denominator, and so therefore, y22, the minimum the denominator can go to is 0. I mean is minimum y22 can go to is 0, and therefore, gain as possible means y22 must be equal to 0. Why is y22 negative not acceptable? You will again end up with the same kind of instability problems that you, right, for some values of GL, this y2 negative y22 will cancel with the GL and then cause an output gain which is infinite. Okay. And so, if y22 is 0, then the network, this goes away, and the gain therefore becomes minus y21 times RL or y21 by YL. Okay. So, all right, and so now if you want the gain to be for a given RL, if you want the gain to be as large as possible, what should you do? What do you want for y21? Yeah, y21 must be as large as possible. Does it make sense? Therefore, the incremental Y matrix of that nonlinear 2 port must look like this. Y11 must be 0, Y12 must be 0, Y21 must be large, Y22 must be 0. Okay. So, these must be the incremental parameters of an amplifier.